Okay, this is our first charge distribution problem that we're looking at together. And I'm going to start with something really simple that has a ton of symmetry. So we're just looking at a simple line charge of length L, and our point of interest is point P, which is right on the perpendicular bisector of the rod. So kind of take a moment and take in the problem, draw yourself a diagram of the problem, and be sure that it makes sense to you. So just kind of take a moment for that, draw yourself a diagram, and pay a lot of attention to this box up here. And that is the problem in and of itself. Okay, let's go ahead and talk about setup then. So when we first are looking at something like this, our approach is going to be that we know that we're going to have to integrate, but I want us to think about what we're integrating. So our given equation up here, notice that we're still using this equation. This is on purpose. So this is equation for the electric field due to a point charge. The reason we're using this is that we are going to conceptualize a charge distribution as being made up of an infinite number of point charges. So this approach then would indicate summation, or integration is what we're going to be using, which is just kind of a fancy way of summing. We'll sum all the contributions of the individual point charges that make up the distribution. So in this case, it's just a one-dimensional distribution along the line. Okay, so I'll start with this given equation, but I need to write it in a differential form. So whereas the problems we were looking at before, the point charge was our total charge, that was all we were looking at. Now the point charge is a differential element of the overall charged object. So whereas before we had E, now what we're going to have is dE. The electric field due to one point charge is just a differential element, or a small contribution of the total electric field. So we'll call that dE. And the other side of the equation, K is our constant. So Q turns into dQ. So we're going to conceptualize or imagine dQ then as a point charge, just one of many charges that make up our charge distribution. And for you guys, I want you to, this is physics, right? This is not math. And I'm going to keep making that point with you guys. So I want you to always, and I mean always in these problems, mark out for yourself exactly, define what dq is, define a dq. You're not going to define every single one because there's an infinite number, right? But um, so I will choose, I'm going to use red when I do this. I'm going to say, all right, I'm just going to indicate in here, and I'm drawing this large. Of course, it would be really small for calculus, right? It would be infinitesimally small, but I want you to be able to think about it, like connect to it physically. So I'm going to draw it a little bit big. This little thing in here, that is my dq. So what you're going to imagine is you're going to imagine that you're going to actually be adding up all the DQs along this line. So in your mind, you have to think about moving up and down or back and forth across this rod, or really just from one side to the other as you're summing. When you choose a DQ to define, though, it's best not to choose one that's in a really special spot. So it's best not to choose one that's on the very end of the rod, at the beginning or the end, or right in the middle. Those are often, the reason those aren't best to choose is that they're often really easy to define. And so you can miss the robust definition that you need for an awkward point. So after making enough mistakes like that when I was first learning physics, I just decided I'm always going to choose like the most awkward point I can see and define the heck out of it. And then I know I can work with any other point in my distribution. So that'll be my DQ. And now I want to look at point P up here. I'm going to switch my colors out actually. So if I look at my equation, dE equals k dq over r squared, this is the equation I'm using, right? So I care about what everything is. dq is a little piece of charge on my charge distribution. And remember what r is. R is the distance between that point charge, the source charge, and your point of interest. So in our case here, R is going to be the distance between dq and P. So this is the same way that you used R before when you were looking at point charges. So lean on everything you can do with point charges as you move to this new method. This is just, you're really adding some math to that, but the concept is largely the same. Okay, so we've drawn in the dq, we've drawn in our R, and now I want you to think about your dE. And yes, I want this to be drawn in to your diagram as well. So dE is, let's pause and think about what that is. That is the electric field contribution that is caused by dq at point P. So dq is just a little point charge, right? At the location of P, it causes, here we're told this is a positively charged rod, so I can conceptualize dq as a positive point charge. So that means radially outward electric field. So at point P, my dE looks like this. That's my dE. All right. Okay. So those are all the things I want. Every single charge distribution problem that you do, I want you to draw those in. Every single one. And if I was teaching this in class, I would be walking around, I'd be looking at your papers, and I'd be asking you to draw every single one of those things in. And on the next exam, when you have your diagrams with your supporting work, the diagrams are going to be worth points, and these things are going to be worth points as well. Okay, so let's get to our place where we need to be to start figuring this out. Notice we haven't even started any kind of integration. That's because it would be totally meaningless until we get these things figured out physically. So this is, again, really different from your experience doing integrals in math. I'm going to define an angle. I know I'm going to need that, right? I can see by looking at this dE what's going to happen here. So I'll go ahead and define this angle in here. I'll call this phi. And now in your mind, take that dq and move it back and forth along the rod and think about what dE does. Okay, so notice point P is a point that has high symmetry, right? So if I move dq back and forth there, what's going to happen with that dE? Just kind of move that around in your mind. I'm going to let you think about it. Okay, so let's go ahead and proceed, and we'll come back to our diagram there. I need a coordinate system. So I'm going to say positive y is upward. I'm going to have positive x be leftward. I've just been drawing, the way I've been drawing things in my diagram. One of the things that I could do due to the symmetry in this problem is just kind of work on the left-hand side of the rod, and I could double that in order to represent the entire rod. That's not always true, but it's true for this particular problem. All right, so I have a coordinate system. I know where my origin is. My origin is right in the middle of this rod, right? And I'll go ahead and start then thinking about my dq. So first move here then is to define dq. Super important. We'll always do that. The reason is that you can't just like start your integral with respect to dq. You're never going to do that in these problems. So what we do is we think about dq, like as I move from one point charge to the other on just this distribution, notice that I'm moving along x. So x is a really, really convenient way for me to get across my distribution and sum it all up. I can just kind of go with changes in x. And I notice also that dE changes as x changes, right? As I move along x. So I'm going to redefine dq here so I can actually execute this integration. And I'm going to call it lambda dx. And hopefully you're on board with what lambda is. I'll remind you that lambda is charge per unit length. So for this particular problem, we have lambda equals q over L. So that's known. We can write that in terms of givens. I like to use charge densities for these problems. I think it's kind of an elegant approach. It keeps my life a little bit more simple. And then I'll go ahead and swap back out for Q over L later. But for right now, I dig having that lambda in there. So you should know charge distribution for charge per length, charge per area, and charge per volume. We'll be using eventually all three of those. Okay, so that's how I can write my DQ. So I'm going to leave that alone. Now, my next job here is to define R. So notice that a lot of what I'm doing is I'm hanging out with this equation up here, right? This is the equation that I know I'm going to be integrating, but it's not ready to be integrated in that form. So I need to substitute into that general form different properties of my specific case. And that's always what we do when we do physics. So if I'm going to define R in this case, I see that conveniently it's part of a right triangle. So that's pretty cool. Then I can say R is equal to the square root of, now I'm going to write this and see if you follow me, x squared plus 2/3 L squared. Okay. So that entails you understanding what x is. Look at the coordinate system. I'll go ahead and pop x in there. So x is, of course, measured from the origin, which is my x equals 0, but you might not know where it's measured to. It's measured to our differential element. So that's what x's job is. X locates the differential element with respect to the coordinate system. R locates the differential element with respect to the point of interest. I'm going to say that one more time. X locates the differential element, dq, with respect to our coordinate system, which we choose every time. R locates the differential element with respect to the point of interest. Okay, different roles. We're connecting them here when we define R. All right, so we've got R defined. Now I want us to think about cancellation. Of course, you can see as you move your DQ around, this DE is going to make kind of a fan up there on top. And every DE, like this one here that's shown that's pointing to the right, it's going to have a partner in symmetry that's exactly equal to it along the line of symmetry being the y-axis there. Yeah. So that means that all of our horizontal components are going to cancel. So kind of take that in. Right? All of our horizontal components are going to cancel. We're going to only be left with vertical components. So what I call the terminology I use for that is a surviving component. So what I say here is we define DQ, define R, and then we define what we're going to call our surviving component, because that's the only component we care about. Okay. Now, in order to do that, I'm going to go ahead and label this angle up here phi, right? And the surviving component of every DE is only the vertical component. The surviving component of every DE, and every DE, I mean, as you slide along this charge distribution and consider every single DQ. Every DQ creates a DE. Every DE has a partner on the other side such that all the horizontal components cancel. So we are only left with the vertical component, such that the surviving component I can define as DE. So look at it, cosine phi. Okay, so now I know that I'm not actually just adding up all the DEs blindly, because if I were to do that, I would do the wrong thing, right? I would not take into consideration that there is cancellation. And for these problems, you must consider that. It's up to you to consider that. You are smart, the math is not. So you have to set that up. So DE cosine phi here, and then we can define our cosine phi. So look at the right triangle there, right? So that'll be 2/3 L over R. And then we can simplify that. We have R in terms of x squared and L, right? So let's go ahead and write this out now. So I'll sub in for R at the end. When I'm going to calculate my E, I know that I want to add up not just the DEs blindly, but I just want to sum the surviving component. So let's think about it this way. My electric field at point P, I want to add up all the DE cosine Phys. That's what I want. Yeah. So that is a way I can write that. It's that's going to be 2/3 L over R, right? Yeah. So 2L over 3R times DE. Now remember for DE, remember what that was. So 2L over 3R. And now let's sub in for DE. DE is going to be then K dq over R squared. So K, in place of dq, we have lambda dx over R squared. Okay, cool. Now let's kind of keep going with that. I want to point out real quick about the lambda dx. I'm going to go back actually to our other page because maybe I flew through this. So this lambda dx, if lambda here is charge per unit length, and I multiply that by a length, I just want to kind of have you think about, I'll just say here, think about dimensions when you're doing this piece here. So this is dq. I know that it has to be charged. So like if it were units, I know it has to be coulombs, for instance. So my lambda would be charge per length or coulombs per meter. I multiply that by meters. I end up with coulombs. Always do that little check when you're figuring out your dq. All right, back to this then. So E at point P. Then we can kind of make this a little bit cuter. 2L K lambda dx over 3R cubed. And I know in this particular case that lambda is equal to Q over L. So I could sub that in if I wanted to now. Then I would have, there's no like one way that you have to do this, but you should understand what you're doing when you do every step here. So this will just simplify a little bit because the L goes away. I think that's why I like it. 2KQ dx over 3R cubed. And remember, we have R in terms of X. So I'm going to say here where R is equal to square root X squared plus 2/3 L squared. So now I'm going to sub that in. So we're getting a little bit more serious here. E at P equals, I'm going to pull some stuff out in the front, 2KQ over 3. And now I'll go dx, leave some space for writing that R cubed here. That R cubed is going to look like X squared plus 2L over 3 squared, the whole thing to the 3/2 power. So it's to the 3/2 power because R is cubed, yeah, and R is to the 1/2 power. So that makes it to the 3/2 power. So I need bounds on this integral. I'm going to expect that from you. You should know where you're starting to sum and where you're finishing, and this should relate to your coordinate system. So if we go back to our diagram, we look at our coordinate system, I see that if I start on the right-hand side, we always go from lower to higher, right? So I would start at x equals negative L over 2, and I finish summing at x equal 2. So negative L over 2, and I go to L over 2. Remember that the bounds of your integration always relate to what you're integrating with respect to. So in this case, we're integrating with respect to x. That's the most straightforward choice. So my bounds are going to be about x. Another thing I can do if I want to take advantage of symmetry here is I could just say, well, actually what I'm going to do is I'm going to double the whole thing. So put a 2 in front of there. And then just go from 0 to L over 2. So there's a slight advantage there. Subbing in 0, it's kind of cool, right? Can make your life easier. It depends on the problem, but for this one, I think it does. So x squared plus Here, this doesn't change my 2L over 3, that whole quantity to the 3 halves. All right. So now I think I have something I can work with. So we've just done like most of the physics. Most of the physics is done right now. So notice where we just spent our time. We spent our time defining the problem, putting a sign convention and coordinate system on our problem, which is necessary. You cannot solve this without a coordinate system. Can't be done. And after that coordinate system, we just defined everything we needed to do. And now I have this integral. So I'm going to leave the integration to you to solve. That is not going to be the hard part. You'll have tables at your disposal for the next exam. Those are up in Canvas. I would suggest that you get to know the type of table that we use in the class and just use that for doing your problem. If you look at the written solution, it has everything all finished all the way toward the end, to the end here. And of course, you'd want vector notation at the end because I'm asking you for a vector quantity, the electric field.